Now let's look a bit closer into cross-entropy by switching to a different example. Let's say we have 3 doors. And no, this is not the Monty Hall problem. We have the green door, the red door, and the blue door. And behind each door we could have a gift or not have a gift. And the probabilities of there being a gift behind each door is 0.8 for the first one, 0.7 for the second one, and 0.1 for the third one. So for example, behind the green door, there's an 80% probability of there being a gift and a 20% probability of there not being a gift. So we can put the information in this table where the probabilities of there being a gift are given in the top row and the probabilities of there not being a gift are given in the bottom row. So let's say we want to make a bet on the outcome. So we want to try to figure out what is the most likely scenario here. And for that, we'll assume they're independent events. In this case, the most likely scenario is just obtained by picking the largest probability in each column. So for the first door, it's more likely to have a gift than not have a gift. So we'll say there's a gift behind the first door. For the second door, it's also more likely that there's a gift. So we'll say there's a gift behind the second door. And for the third door, it's much more likely that there's no gift. So we'll say there's no gift behind the third door. And as the events are independent, the probability for this whole arrangement is the product of the 3 probabilities, which is 0.8 times 0.7 times 0.9, which ends up being 0.504, which is roughly 50%. So let's look at all the possible scenarios in the table. Here's a table with all the possible scenarios for each door, and there are 8 scenarios since each door gives us 2 possibilities each, and there are 3 doors. So we do as before to obtain the probability of each arrangement by multiplying the 3 independent probabilities to get these numbers. You can check that these numbers add to 1. And from the last video we learned that the negative of the logarithm of the probability is the cross-entropy. So let's go ahead and calculate the cross-entropy. And notice that the events with high probability have low cross-entropy and the events with low probability have high cross-entropy. For example, the second row, which has probability of 0.504, gives a small cross-entropy of 0.69. And the second to last row, which is very, very unlikely, has a probability of 0.006, gives a cross-entropy of 5.12. So let's actually calculate a formula for the cross-entropy. Here we have our 3 doors, and our sample scenario said that there's a gift behind the first and second doors, and no gift behind the third door. Recall that the probabilities of these events happening are 0.8 for a gift behind the first door, 0.7 for a gift behind the second door, and 0.9 for no gift behind the third door. So when we calculate the cross-entropy, we get the negative of the logarithm of the product, which is the sum of the negatives of the logarithms of the factors, which is negative logarithm of 0.8 minus logarithm of 0.7 minus logarithm of 0.9. And in order to derive the formula, we'll add some variables. So let's call P1 the probability that there's a gift behind the first door, P2 the probability that there's a gift behind the second door, and P3 the probability there's a gift behind the third door. So this 0.8 here is P1, this 0.7 here is P2, and this 0.9 here is 1 minus P3, since the probability of there not being a gift is 1 minus the probability of there being a gift. And let's have another variable called yi, which will be 1 if there's a present behind the ith door, and 0 if there's no present. So yi is technically the number of presents behind the ith door. In this case, y1 equals 1, y2 equals 1, and y3 equals 0. So we can put all this together and derive a formula for the cross-entropy, and it's this sum. Now let's look at the formula inside the summation. Notice that if there is a present behind the ith door, then yi equals 1. So the first term is logarithm of pi, and the second term is 0. Likewise, if there is no present behind the ith door, then yi is 0. So this first term is 0, and this term is precisely logarithm of 1 minus pi. Therefore, this formula really encompasses the sums of the negatives of the logarithms, which is precisely the cross-entropy. So the cross-entropy really tells us when 2 vectors are similar or different. For example, if you calculate the cross-entropy of the pair 1, 1, 0 and 0.8.7.1, we get 0.69. And that is low because 1, 1, 0 is a similar vector to 0.8.7.1, which means that the arrangement of gifts given by the first set of numbers is likely to happen based on the probabilities given by the second set of numbers. But on the other hand, if we calculate the cross entropy of the pairs 0, 0, 1 and 0.8, 0.7, 0.1, that is 5.12, which is very high. This is because the arrangement of gifts being given by the first set of numbers is very unlikely to happen from the probabilities given by the second set of numbers.